In this video, we're going to study one of the most important concepts in this module, and it's the one of the limit of a sequence. Before we do that, I want us to take a look at an example to illustrate what we want the limit to be. So let's consider this sequence of an equals 1 over n. So what should the limit as n goes to infinity of 1 over n be? Well, here we have a graph. As you can see, we have here that as n gets very, very large, the values of my an's gets very, very close to 0. So what I'm saying is that if n is very, very large, then 1 over n is very, very close to 0. So my guess is that the limit should be 0. Okay, we'll need to make this formal. That's kind of a fun idea. So the intuitive idea of the limit of the sequence a n as n approaches infinity equals to L means that if n is large enough, we can make a n as close as we like to L. Okay, so if n is large enough, we can make a n as close as we like to L. Good, but then we need to understand what this means. Well, a n is close to L means that the distance between a n and L is less than epsilon. And we use the absolute values to denote distances between two real numbers. So a n is close to L would mean that the distance between a n minus L is less than epsilon, where epsilon is something small. I haven't told you what epsilon is yet, but well, if the distance is smaller than a small number, then they're close, right? Okay, so that's what we'll do. And then n large means that n is bigger than some number, right? Being large is something that is a comparative term. So n large means that n is bigger than some like cutoff number. Okay, so we can write if n is large, then a n is close to L as, well, if n is greater than capital N, then the absolute value of a n minus L is less than epsilon. Okay, so we have these, and let's see how we can improve this. Here we have the graph of a sequence, and remember, we want to capture formally the idea that if n is large enough, then I can make a n as close to L as I like. Okay, so let's look at this. So if n is large, then the distance between a n and L is less than epsilon, where epsilon is some small number. So let's see how we can capture the right-hand side of this implication. You see, the distance between a n and L is less than epsilon, which means that the dots are within this blue band that I'm creating here. But you see, for example, the first dot here, A1, is inside that blue band, but the next one, A2, is not. So here we're saying, well, if n is large enough, we can make things happen. So if we look at it, we're going to look at all these dots and see after which point all of them are within that blue band. And here we can see, here I found this n, and you will see that after that point n, all the dots are indeed inside that blue band that I created. But you see, here I'm making it close. I chose some epsilon, some distance between a n and L. I chose it. Okay, good. But I said that I want a n to be as close as we like to L. So that means, okay, I chose this distance, but if someone chooses a smaller distance, this has to work as well. So to make it as close as we like, well, it has to be for any distance, even if it's teeny, 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 tiny. So for any epsilon positive, this would have to work. So you see, now if I choose smaller epsilon, like this, now, because my blue band is smaller, it's thinner, some of the dots that were previously trapped by the thicker blue band now escaping. Like you can see here, we have several dots that are now outside. Okay, but I said that if n is large enough, then I can make a n as close to L as I like. Okay, then, well, what I'm going to do is I'm going to look if we see I can find another n. Maybe the n needs to be bigger. If I push it a bit, what happens? Well, You see, now I found a greater n is bigger now, such that indeed after that point, all the terms of my sequence are inside that epsilon band, that blue band. So you see, this choice of n depends on my choice of epsilon. And it's enough to find one, right? After I find one and I know that all the terms after that point are within that blue band, I'm happy. So the way to complete this would be that, well, for every epsilon positive, there exists a natural number or a real number, doesn't matter really, you will see that in the exercises, such that if n is greater than capital N, then the distance between an and L is less than epsilon. So very good. So here we have an idea of what should happen, and we wrote a definition. Now let's collect it all in one place and write it formally. The definition is, well, the sequence an converges to L if and only if for every epsilon positive there exists a real number n such that if n is greater than this capital N, then the distance between an and L is less than epsilon. Excellent. So how can we read this? With meaning. Remember, whenever you see a new definition, try to read it carefully with meaning to make sure that you understand it. Well, the first bit says that no matter how small epsilon is, there is a point such that after that point, all the terms by n are within epsilon of L. So try to remember what it means. You need to go back to the pictures where I was showing you that I made epsilon smaller. It forces me to find a bigger n. And that is going to be the idea behind many of the proofs in analysis. In terms of notation, we can write it as the limit as n approaches infinity of an equals L. But we can also write just an and like a little arrow L. That means an tends to L. And sometimes we write an tends to L as n tends to infinity. Those are the three most common notations for this. And now I have a new definition, is convergent sequence. So far we had shown that the limit is equal to something. That's the definition that we have. But now in general, we said that a sequence is convergent if it has a limit, if the limit exists. So what that means is that a sequence is convergent if there exists a real number such that that real number is the limit of my sequence. So there exists a real number such that for every epsilon positive there exists an n such that if n is greater than n, then the distance between an and L is less than epsilon. And if you see here, there are lots of quantifiers here, there's lots of things going on. So try to sit down and think about the order, what they mean, and how we can interpret it carefully. Okay, now, whenever we learned a concept of something is something, right, like here, the sequence is convergent, well, there must be some objects that are not convergent, some sequences that are not convergent, because if all sequences were convergent, that definition would be really pointless, right? So, what does it mean for a sequence to be not convergent? Well, a sequence is divergent if it doesn't have a limit. I'm going to give you here some examples. Remember, the limit has to be a real number. So if it tends to infinity, infinity is not a real number, so we cannot say that the sequence converges. And the same thing, if we have a sequence that converges to negative infinity, we cannot say really that it converges. So it is wrong to say converges to negative infinity. We just say diverges to negative infinity. And the same thing with the an, diverges to positive infinity. Because as I said, convergence means that you get close to a real number, and positive infinity, negative infinity are not real numbers, so we're not allowed to do that. But of course, there's another possibility, and it's that our sequence does weird things, like could be oscillating. So here we have three examples of like the three main ways in which a sequence could be divergent. Now, your task would be to write down the definition of a divergent sequence using quantifiers. To do that, you need to go to the definition of convergent sequence and negate it. Being careful of making sure that everything is in the right order and that you're negating everything correctly. Please just give it a go, and if you have any questions, just let me know.